So this is a little chapter on polymers. A lot of this chapter is really sort of just telling you how they're put together, but also just introducing you to a lot of very common polymers so that you can sort of appreciate what's happening here. So there's a lot of, just learning about these different types of polymers in this chapter. So there's really no math and that kind of thing. So hopefully you can learn about these different polymers and appreciate what they are. And of course, you'll realize how many of them you use. So what is a polymer? Well, these are really big molecules. And later on in the semester, when we talk about food and that sort of thing, we will learn about your polymers. You're made up of, 3 types of polymers plus fats. And the rules that come to play with these polymers are the same as the ones that make up you. So these are what we say macromolecules, and they're huge, 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 huge structures. What does it mean? Well, it's a Greek word, so poly means many, right? You probably know that. And mer is from meros, it's the part, right? So many parts. And they're made up of these smaller units and they repeat, right? So here you can see polystyrene. Poly means many styrenes, and this is what styrene looks like. You know now this is a benzene ring and there's a methyl group here. And they're joined here over and over and over again. We'll talk a little bit how it's made. So styrene itself is this, and you'll see this very often with polymers, that there happens sometimes or oftentimes a double bond here. So this then allows it to join to the next polystyrene, right? So you can see that. So technically polystyrene is a benzene ring with an ethene attached to it, right? And you know a little bit about that because of organic, right? And they come together, and we'll go over the different ways that this can happen, right? So polymerization then means the joining of these monomers to make a polymer, all right? So, of course, there are many natural polymers. I just said that you yourself are made up of several of these, and there's a couple of them are listed here. Proteins, starch, of course, for you, starch is actually called glycogen, but this is what you'd find in plants, right? So wood, cellulose, you're not made up of cellulose. The other one that's not listed here, of course, is DNA. But here you have some very common ones. So starch, wood, proteins, cotton, right, is a polymer, and silk is another, all right? So those are natural ones that are made without our help, right? And then, of course, we've learned to make them. And the very first polymer was actually made from a natural product. Later on, I'm going to talk about the first polymer, synthetic polymer. But the first one here was celluloid, and we don't use it as much right now because it's flammable and it caused problems. But we still see this. It's actually made from cellulose, right? So cellulose is a plant polymer right there. See, wood is a type of cellulose as well as what makes up most plants. That's, they don't have a skeleton, they have cellulose. So this is, what they did is they treated it with nitric acid, as you can see here. And so cellulose nitrate, what did we use it for? Well, billiard balls, right? They used to be made out of ivory. And that, of course, is not sustainable. You could see men's fashion collars, and probably the most famous would be celluloid for movie film. So you might even see it referred to, whoever was on celluloid, that would have meant that they were in the early movies. And it's used today, all right? So here's some examples, right? Guitar picks. But this one wasn't the first completely synthetic one. We'll talk about that one in a sec. So phenol, formaldehyde resins, those are the first ones, and we'll get to that. So polyethylene, though, is probably the most common synthetic polymer. It's obviously plastic, one of the many types of plastic, so polyethylene, and there's different forms of it. So again, here you can see, your a bit of your organic now. So ethylene, right? So ethene, ethylene. So you have an ethyl with double bonds. That double bond then joins, and then you make poly out of it. So it really is a very, 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 very long alkane, right? At the end of the day, and that's what you got. So we've got carbon and hydrogen. So very, very common plastic. And it can be made into many different things, all right? It is a petroleum product, all right? So you can see in my notes, what was it used for initially? So it's obviously the simplest one that you can make, right? There's nothing hanging off of here. It's very tough and flexible. And interestingly enough, it was the first electric insulator for radar cable, which was really important. Then I have this little note about, so I'm looking at my notes, page 2. So it was used to insulate radar cable, and that was, at that, when radar was being developed, it was top secret. So it was just kind of an interesting kind of way of looking at it. Then prior to polyethylene, the cables were insulated with natural rubber or cotton, right? So you can see how that would be a problem during the war, because we could monitor, or you could limit access to those two things, because natural rubber obviously comes from rubber tree, cotton, right? So here you could make something synthetically, very simply, and that was really quite an advantage, especially on something that was top secret. So polyethylene comes in a couple of forms now. So the high density polyethylene, and you might see this labeled on your plastics, HDPE, right? That's here, the molecules are linear and they pack close together. So you can just read this off my slide, but it's used for milk jugs, bottle caps and stuff like that. So you'll notice very often the bottle caps, which seem to be getting smaller and smaller these days and harder to get off, because they're limiting, I guess, that plastic is probably more expensive to make. Then there's low density polyethylene, which is more highly branched, okay? And that's used to make more flexible things. So you can see here plastic film, plastic bags, electric wire, insulation, that kind of thing, all right? So the degree of branching can really make a difference. Now, here's something to look at. These are two terms, and I want you to think about what they mean, all right? So how to put polymers together, all right, to make things out of them. And they will differ, like different types of plastics can be used, or polymers can be used for different things. So the word plastic, all right, the word plastic itself means that it is bendable, all right? Whereas setting means that it's fixed, all right? So here what you're using is thermo, so heat, so thermoplastic, right? So what's happening here is that these polymers, they soften when they're heated, okay? So polyethylene is one of those, all right? Other polymers will behave differently, all right? So what will happen with them, they're heated to harden, all right? And they don't soften afterwards upon heating, right? So you can sort of see the difference in what they're used for. So Lego blocks, they will can be melted down and used over and over again, but thermosetted ones won't. So eventually what they'll do is just break down, right? So this is one of the reasons you got to sort your plastics when you're recycling, and it's actually gotten so complicated for people that it's actually easier for them to sort it for you. But you can see sort of the difference. So you can see here with something that gets heated in use. So here you can see with electronics, you wouldn't want it to get softer when it's heated. So these will not soften on heating. So eventually they'll just discolor and they'll break apart. I don't know how long they might take to decompose, but clearly a different type of thing. So you can't remold these, but the thermoplastic ones you can, all right? Now, in terms of forming the polymers, there's two main ways of doing it. And the first one, the addition polymerization, this doesn't work in your body. Here what's happening when the monomers are put together, they are put together in such a way that you don't lose anything. So all of the atoms that are in the monomer are conserved in the polymer, right? So these are addition polymers, and many of them are made out of polyethylene, and the hallmark there is that you've got a double bond in the monomer in some way so that you can just flip that bond and make it join to the next carbon or the next part of the molecule. Condensation polymers, on the other hand, these are what happen in your body when you make your proteins and your glycogen and your DNA. nucleic acids, you lose something in the formation, and specifically you use water. So it's a dehydration reaction. But when it comes to just in general chemicals or these polymers that are made, you're losing something. So I mentioned water. You can also lose alcohol or ammonia or even hydrochloric acid, depending on what the polymer is released. So those are byproducts of the polymerization. So you see the difference. Addition, you're not losing anything. Condensation, you are. All right. And I've listed some in my notes. So condensation polymers would include nylon, polyester, and resins, where addition polymers, polyethylene, polystyrene, polyvinyl, teflon, which we're going to talk about as we go through this. So you'll see as we go through the slides, there's all kinds of different examples of these polymers that you can encounter. So many of them are plastics, these addition polymers. So polystyrene, you can sort of see that the way that looks. You can see there's an ethyl group with we just talked about this at the beginning, with an aromatic or a benzene ring on it. Again, you've got your double bond so that you don't need to lose anything in the formation. What do we use polystyrene for? Well, all kinds of stuff. Toys, plastic cups, styrofoam. That's why it's called styrofoam, from the styrene, right? So it's, made up packing materials, insulation, polypropylene. Okay, here you're talking about prop. So now you have one extra carbon to the ethylene, right? So because now you're at 3 carbons. This is now a very different type of plastic. So you can see it resists moisture because it's a longer hydrocarbon, right? Oils and solvents, they use that to make luggage and battery cases, all right? So you can see the different types of polymers are amenable to different types of products. Now, other ones, polyvinyls. So what does that mean? So look what you've got here. So on your ethylene, now you've got a chlorine. So you've got this halogen as a functional group on here. Now you've got completely different properties again. Now you've got clear plastics, plastic wrap, plumbing, artificial leather, right? That's always vinyl, floor tiles, shower curtains, very different types of properties, but very, very prevalent. So PVC, polyvinyl chloride. So when you see the term PVC, that's what it stands for. And now you know that it's basically the monomer is an ethyl with a chlorine attached to it instead of a hydrogen, and that gives it different properties. All right. PTFE, that's Teflon, right? So here another addition polymer. Notice here what you're dealing with is a series of methyl groups where the hydrogens have been replaced with fluorines. Fluorine, remember, it's a halogen. It's got the 7 electrons. Doesn't want to react with much. It's quite happy being bound to the carbon, so it's pretty non-reactive, which is why it's Teflon, right? That's what you want for your Teflon. You've got your coatings. Interestingly enough, and I did not know this, but it was discovered by accident, right? So what ended up happening is that chlorine gas solidified and it coated the container. And then they were like, wow, nothing sticks to this. It makes it sound like a lot of organic things were discovered by accident, which they were, ironically. But of course, the person who did that was working for DuPont, so that was quite lucrative for that company. Polyacetylene. Now here, this is one of those polymers that retains the double bond, so it's reactive. So notice that it will conduct electricity due to those free electrons, all right? So it's a conducting polymer. You can see most of the ones that we just talked about, everything is bonded up and rigid. I mean, not rigid in terms of the structure, but in terms of the electron movement. As you know, movement of electrons means movement of electricity. And usually if they can't move the electrons, we're insulated. And here, all your electrons are really fixed, right? It's extremely non-reactive. Now here, you have a situation where you've got double bonds, you have free electrons, so yes, it's conductive. But most polymers are insulators, all right? Then nylon, that's probably one of the most famous ones. Another one that was discovered by accident, and oh, lo and behold, yes, DuPont, right? I think those chemists were having a lot of fun in that company because they were discovering all these really cool things, and they're like, well, what can we use this for? But most of our synthetic fibers are based on nylon, right? So here you can see it's a reaction with a carboxylic acid, all right? So now we're dealing with the condensation polymers, so we're losing something. So when you're making nylon, you're releasing water, right? So an amide with a carboxylic acid, you release water. That happens in the body too, amides with carboxylic acids. Yeah, so they're named, ironically, by the number of carbons in the monomers. And then polyesters, right? That's another one that's used for clothing. The interesting idea here now, instead of mixing an amide with a carboxylic acid, they started playing around. They mixed an alcohol with a carboxylic acid. And this one does not absorb water and it's quick drying, right? So that's why it's used for your workout clothing. Film coatings, so it's mildew resistant because it repels water. Mylar is, you know, what its trade name is. All right, so yeah. Now here, phenol formaldehyde resin. Now this one was called bakelite. This was the first synthetic polymer made, and it was used as a thermosetting resin, right? So it really makes a beautiful complex network. That's why it would be a resin or a coating. And you can sort of see the structure here. It's quite complex. So it's named after the person who patented it. So Leo Baekeland. I don't even know if that's how you pronounce his name, but there you have it. So you can see back in 1909, so first synthetic polymer. So that's even before the First World War. And it was, you know, I'm trying to think of something really obvious that, you know, bakelite is used for even now. And I just didn't see if I put something in my notes. I didn't. But yeah, thermosetting. And remember what we said, thermosetting, you heat it and then it becomes hard. So you can sort of see, and then you can't, you know, heat it again and have it, you know, become soft again. So you can see that that would be important if you're using it as a coating and a protectant. Which is what it was used for. Now, molding plastics, all right? So you know that there's all kinds of different types of forms that our plastics take to make all of the things that we use plastic for. So there's 4 ways in which they're formed. So one would be compression molding, which as it sounds, you heat and pressure applied directly to make the polymer shape, right? It starts off with a powder. And as you push things together, it's also going to heat because of the reaction taking place. Injection molding, I think that's the one probably we're most familiar with. Melted is forced into a mold, and then it cools to set. Extrusion molding is the opposite. So you're pushing it out of a mold or out of a form to make a shape. So it's, you know, the form is called a die. And then blow molding is a process where you're blowing air into it and the polymer sticks out to the edges of the mold. And that's how they make plastic bottles. All right. I don't know how familiar you guys are with dyes. Back in the day when I was really young, I dated a guy who was learning to be a tool and die maker. So yeah, that's basically a form, and then they use it to make cars, different dyes. Anyways, notice it's not spelled as in the color, D-Y-E, different kind of thing, all right? Now, rubber and elastomers. So here, the critical thing here is the word elastic. So what this means is that it can change shape and bounce back, right? So this was really important. You know, because they were trying to replace natural rubber. Actually, if you know, I don't know if you know this, but natural rubber is from a tree, the rubber tree. It's a natural isoprene unit. This is what it looks like. You can see there's double bonds in there. It bounces back, right? So it can elongate and then it will return to its original shape, which is incredibly important. But obviously can't keep using the tree. So they had to synthesize this. So who was the first one to do this successfully into a way that it could be used? Hello, Goodyear, Charles Goodyear, and you know, tires, right? So because natural rubber was really soft and tacky, he discovered this process called vulcanization, and all that means is that you're going to cross-link it with sulfur groups. And if you look at it here, they've got some double bonds. Remember, sulfur likes to form 2 bonds. It's like oxygen. It's a valence of 6. So it could easily form a bond here and then to another one on another part of the polymer and sort of cross-link it, right, as you can see here. And this was patented, obviously, and used to make tires, right? So first it was used for natural rubber, and it's used even now. It's called vulcanization. So it makes a harder, more resilient rubber. Now, synthetic rubbers, there's several different types, and you can see, so synthetic rubber, the original, I don't know if this is the original. I mean, I'm making that up. I'm not sure. I'm just guessing because it's very similar to polyisoprene, which is the natural one. If you look at it here, right? So you can see it's crossed. It's got a branch off of it. Here, it doesn't. So this one be called polybutadiene. Then, of course, neoprene, right? Notice here there's a chloride group, so that gives it different properties. It's similar, right? But now you've got this chlorine in place of the methyl group, all right, that you would have seen back here, right? So you've got this chlorine instead. Whoops, going the wrong way. And gives very different properties, right? So you know what they use that for, right? And then, of course, styrene-butadiene rubber. So here you're sort of combining things. So you have a butadiene, then a styrene, then a butadiene, then another butadiene. So they threw some styrenes in there. So here you can see 25% styrene, 75% butadiene. So the interesting thing here is that they can make different proportions of these and get different types of properties. So this 25-75 mix is, here they say it's tougher and more resistant to oxidation than natural rubber, but mechanical properties are less satisfactory. So, oh, excuse me. You can see they were playing around with this to see what kind of properties they could get out of this. Now, what kind of things do we have? So neoprene, of course, wetsuits, right? Styrene-butadiene, right here, you've got them in the hiking boots, and polybutadiene. Now they use that for tires. Instead of having to take natural rubber and vulcanizing it. So there you go. Now, elastomers, all right, so these we refer to as binders, right? So again, there's the word elastic in there, right? So that means that they're more resilient, they can be flexed, and notice they're much more resistant to cracking, right? Which is why they're used for latex paints, right? So, you don't want the paint on your wall to dry out and flake. Eventually, some of them do, but this is sort of the idea here. And importantly, look at this. It's using water as a solvent, right? So that's why you can wash it off. So it's better than oil-based. Then you have polyurethanes. These are similar to nylon, right? So again, polyurethanes, rubber, right? Skate wheels, these are different types of things, furniture, finishes, and that kind of thing. So these are both elastomers. We don't want flaking taking place in both of these cases. Now, composites. A composite obviously means that you're mixing things together. So here you're using your high strength fibers, and you're going to hold them in a matrix made up by a polymer, right? And there's so many different ones of these, but they're quite strong and light, which is the other thing. So you can see how they're being used now for boats, tennis rackets, parts of automobiles. There used to be a type of car, still see them around. My husband tells me they don't make them anymore, Saturns. I don't know why. I know not very much metal on there, like composites. Fishing rods, right? So things like that. High strength and light. And okay, then of course the next one I listed are silicones. I know this looks pretty freaky. You probably think of silicones more in terms of movie making, but they actually, you can make them so lifelike that they're being used for prosthetics for people. Now, silicones, here you're dealing with a polymer that's not based on carbon, it's based on silica. So this is going back to what I was saying the other day, or my other video about carbon-based or life forms and that kind of thing, because most of that is based on carbon. But here they've used silica instead, right? So they're polymers that contain silicon rather than carbon. So polysiloxane um, is one. And they really can take on a lot of forms based on their cross-linking. And here's a couple of very common uh, uh, applications, all right? So you can see here the muffin cup things. I had a set of these. I've never used them. Um, and then here, like I said, looks pretty lifelike, but it's there to, be a prosthetic on this person's hand. I had all kinds of other wicked pictures I was going to put in here, and I decided not to do it, but of human body parts. Okay, so properties of polymers. Very high molecular weights, strong fibers, and then there's other ones that are more viscous. So strong ones are going to be, very packed and tight together. Viscous are going to have more branches. Here you can see crystalline ones. As you can tell, crystals are very rigid in their shape. Here amorphous, right, have randomly tangled. And this is going to have to do with the transition temperature, which is kind of an interesting thing here. The temperature at which, above which a polymer is tough and rubbery, and below which it is like glass or hard, brittle, and stiff, which is really kind of weird because polymers, they can switch back and forth depending on which one you're looking at, and they can change their properties depending on how hot they have become. All right. Yeah, so it's kind of an interesting way of looking at it. So in general, properties: high molecular weights, strong intermolecular forces. So you can have strong fibers versus viscous solutions. Crystalline ones, the fibers are aligned and rigid. Amorphous, they're random. And then the glass transition temperature. So just definitions. Now, of course, I don't think the issues with these things are secret. Because these are, not natural things, and they're huge, they take a long time to decompose. 11% of our mass solid waste, 20% of it by volume. And more than half of that solid waste ends up in landfills. Which and nobody wants a garbage dump next to their house. So it's difficult to find a place to put it. And embarrassingly enough, we send a lot of our garbage overseas, which I think we should be really embarrassed about. But anyway, so how do we deal with this? Well, one of the ways to do this is to incinerate them. And when I was taking environmental chemistry, I learned, and I thought this was the coolest thing ever, but apparently where they make cement, the temperatures in those kilns are so high that it can easily get rid of most of our plastics. Even rubber, even tires can go in there. But the problem is the gases that are released. So even though this might be a really interesting way to do it, and the amount of heat being released when those bonds are broken, you can imagine, right? A lot. And that can be used to make electricity. But the thing is, the toxic gases that are released from that. So how do we deal with that? So for example, PVCs, polyvinyl chloride, right? You've got your chloride there, and you've got hydrogen, and you're going to make hydrogen chloride in a gas form. Like, is that what you want? Hydrochloric acid, it's one of our strongest acids. It's so hot, that's a gas. And it would come off of this process. So this is something that would have to be dealt with. You can imagine it could be, right? Just make it a liquid and use it for something else, right? But these are things that have to be dealt with. Degradable plastics, so more and more of it is coming from that. Something really cool, and my daughter finds this super cool. You can make edible plasticware because it's made out of literally biopolymers, so sugar, and then just eat it after you're done with it. So I would imagine you're going to see more and more of these kinds of things in the future. Either that you can biodegrade because they're more natural, or photodegrade, and then recycling, right? Over the long term, just try to reuse them. Of course, those thermosetting ones are going to be harder to reuse, right? The thermoplastics probably be easier because you can melt them and remold them, right? So that goes back to looking at the Lego blocks versus those electric connectors or whatever those things were. Clearly that, I don't do that. But anyways, So then plasticizers, a lot of those things are found in these plastics. They're there to make things flexible, but they're quite volatile, right? So eventually these materials come off, those plasticizers. Your paint eventually will flake, but those plasticizers come into the atmosphere, and one of those plasticizers, probably one you heard of, polychlorinated biphenyls, PCBs. Yeah, dangerous. We don't want those in the environment. So this is a problem, as you can imagine. So now when it comes to green chemistry, I don't have a focus on green chemistry in this chapter because I think it's obvious. But they're trying to take these out of these plastics because we now acknowledge the problems that these have and how prevalent our plastic waste is. So hopefully that helps you and you learn some stuff from that. This is an interesting chapter. I don't think it's technically challenging, just to probably more to just learn all these different types of terms. For that, use the study guide that will help you. But I hope you gain an appreciation for polymers and how prevalent they are and how important they are to your life. All right, so great.